Okay, good afternoon everyone and welcome to the presentation of our paper, An Efficient Ant Colony System for Edge Detection in Image Processing. So first, edge detection is actually referring to the process of identifying points in the image where the brightness of the image changes sharply. And this is a very fundamental procedure in several operations when we talk about image processing, computer vision, machine vision. It has a lot of application in medicine, industry, space mission, and other areas. This is what makes this process very important, and there are several works in the literature which have focused in finding a solution for edge detection. However, this was mostly solved using complex mathematical functions such as the first and second order derivatives or the zero crossing. Those functions, when we use them to solve this problem, they are not only complex, however, they are sensitive to noise. That means that we will be then in need for using filtering techniques, and using such filtering techniques increase the complexity of the process first, and then may lead also to remove edges which we have already found in the image, simply because it may recognize it as noise, and they then will be removed. In our paper, we proposed two versions of ant colony system algorithms which solve the problem of edge detection in an efficient way, producing noise-free binary images. They are referred to as the focused ACS, FACS, and the extended FA6. First, let's start with a general overview of ant colony optimization algorithm. Those are a family of meta-heuristic optimization algorithms which mainly used to solve combinatorial problems, where the problems could actually be represented using graphs. And they are simply inspired from the foraging behavior of ants, where ants search in the environment for food sources, and then they simply deposit pheromone over their paths and pass to the better food sources receive a higher amount of pheromone to attract more ants to use the same path, and over time we will have a path that dominates to the optimal food source. Two ingredients are used for an ant colony optimization algorithm, mainly the exploitation and exploration. Exploitation, where, as I said, ants are using information produced by other ants in which were exploring the environment, and use this to optimize their choices. And exploration here is done in a probabilistic manner, where ants are ants, or here in the algorithm they are referred to as ants, they are the solution, are picking their next step using a probability rule that has also again two components: the heuristic information of my problem plus the pheromone which is used to direct the search. There are several variants of ACO algorithm, like max-min system, ant colony system, latest system, and others. And the selection of any of them to solve our problem is based on the problem itself. And for edge detection problem, which we are discussing in our paper, we have selected the ant colony system. Here, also a brief overview of the differences ant colony system have in general from ACO algorithm. First, it has a different probability transition rule from ACO systems, which you are going to see on the next slide. It's using a kind of global pheromone update. All ACO algorithms actually use pheromone update at the end of each iteration, the solution found in the previous iteration are rewarded in terms of pheromone, and this is called like a pheromone update, and it is an offline operation. By ACS, this is done just to reward the best so far solution or the best solution found in the previous iteration. We have modified this rule in our paper to actually reward each solution found in the previous iteration, simply because it may represent a potential edge which we want to detect in our image. Because normally when we use ACO algorithm and we represent our problem as a graph, we are interested in finding the optimal path in the graph. But here, any found solution may represent actually a potential edge which we are searching for. One of the unique differences of ACS is the use of a local pheromone beside the global pheromone update, where this is a kind of online update to the pheromone. Each enter updates the age it is visiting by reducing the amount of pheromone assigned to that age, for reducing in turn the probability for other ant to pick this age. And in this way, it increases the exploration probability and avoids stagnation problem, which is a well-known problem that can be observed when using ACO algorithm, where the solution is not improving over iterations. Here is the probability transition rule used by ACS, and actually it consists of two parts. First, we have the exploitation, where with probability Q0, we decide to pick the best choice selected based on the pheromone amount and the heuristic information, and with probability 1 minus Q0, we explore for new solution. Here we can see the parameters of this probability rule, where Q is a uniformly distributed variable between 0 and 1. Q0 is a parameter between 0 and 1, and J is given by the traditional probability rule of ACO algorithms, where the probability to move from I to J by nt k at time t is a multiplication between the amount of pheromone deposited on the age to the power of alpha and the heuristic information assigned to that age to the power of beta divided by the summation of this multiplication for all valid neighbors to move to. So now back to the age detection. We said that using any ACO algorithm is normally requiring the transformation of our problem in a graph. Here, our problem is on an image, so we tend to transfer each pixel of this image to represent one vertex of our graph, and then it has the connection to its neighboring pixels of the image, as you can see on the right image, the pixel IG with its 8 neighbors. For this problem, we define our heuristic information as following. The heuristic information are first assigned to each pixel, and the heuristic information associated with pixel ij here is computed using a function designed to compute the intensity variance between the surrounding pixels. So as we see here, for pixel ij, we are just subtracting the intensity of the pixel surrounding it in pairs, and there we are summing this variance in the intensity. The value we obtain, we divide by the maximum intensity variance found in the image. This means that a higher heuristic information is associated with a pixel that has a higher variance in the intensity around it, and this increases the probability to pick this pixel in the next step, because it may be associated with an edge where the brightness of the image changes sharply. There were several works, as I said, in the literature to deal with this problem, and few of them have used ACS, like the one of Betrina, which is also used in our paper to compare our results to. In this work, the authors use actually the ACS direct without any modification to solve edge detection. That means they were using a kind of a random initialization of the ends on the graph that represent their image. Here down we can see it's just a typical image for a test called the Lena image. On the left side we see the uniformly distributed positions of the end, initial position, and then here are some of the iterations obtained by applying the ACS. Completely re-implemented by us because they don't provide the code, however we have similar results to their results, and here is very clear the high level of noise in the binary obtained images, where there is definitely the need for using filtering or thresholding techniques to remove the noise. Here we move to the first then algorithm proposed by us to solve this problem. It's called focused SES, and this algorithm is an efficient one that has the following advantages. First, producing high quality solutions, free of noise binary images with reduced complexity. The core idea of the algorithm is, instead of initializing the ends of the ACS on uniformly distributed position, we initialize our ends on focused or selected positions that are representing promising positions to find our solution. How we select those positions? This works as following. First, we compute our heuristic information, which are computed as shown in the previous slide. This computation is performed offline. Afterwards, we rank our heuristic information and we assign let's say that we have k ends. We assign to the k ends the first k pixels that are associated with the highest heuristic information. This will take care of making the search starts at positions that are associated with the best solutions. We'll obtain at the end a solution with increased quality and with a reduced complexity. Moreover, in the paper we have also tested or performed a parameter sensitivity test for the different parameters used in ACS, where we try to change the values of those parameters, as we can see here on the current slide. And the conclusion was that with changing Q0 and beta, there is no significant change on in the performance of the algorithm, whereas by increasing the values of alpha and tau 0, we preserve edges found in previous iteration. And this is kind of logic because those are the two parameters associated with the pheromone, and that means that we are assigning a higher importance to the pheromone. So we are using or exploiting the information found in previous iteration, preserving the edges. And there were other parameters tested, and we saw that also the time of detecting the edges is mainly a trade-off between the number of ends and the number of iterations. However, we fix our parameters to the values used in the literature paper by Bethina to be able to make a fair comparison between our results and their results. And here again the results obtained from the Bethina ACS algorithm, and at the bottom we see the results obtained by the FACS, where we can see the images or the binary images free of noise with improved performance than the one using direct ACS. We have tried also to use or to check our algorithm for much more complex images, like here the mandrel, using here the Bethina approach, again with random initialization of the end positions, and we see again the high level of noise in the images, which needs actually definitely filtering techniques. And on the bottom you can see the results obtained from the FACS free of noise. However, if you have a look here back, you see that there is actually between, when we use FACS, between the iteration number 8 and 10, if you look carefully, you see that there is no improvement done for or achieved for the solution. And sometimes we are actually facing a stagnation problem when we use FACS. This is because initializing the ends at the same position, sure, when we initialize the ends at uniformly random position, we are covering the maximum possibilities for tracking our solutions. And when we focus or select particular positions, initial position for the ends, even if they are promising positions for better solutions, some of them may lead to no solution, and this may also result in stagnation when using FACS. And for this, we introduce our second algorithm, the extended FACS, which inherits the same advantages as FACS. However, the core idea is that some of the ends are allowed to be reinitialized over iterations. How the reinitialization works, at the end of each iteration we compute the average amount of pheromone deposited on our image. Then ends are ranked based on the quality of their solutions. That means that ends which have deposited a smaller amount of pheromone than the average amount, they are reassigned to new initial positions, and their memories are reset to allow them to revisit positions or pixels which they have already visited. This again increases high quality solutions and solve also the stagnation problem we may face when using FACS. Here we see again the results on the top when using FACS, and on the bottom while using the extended version of ACS, and we see here that we are able to find out much more details or ages on the images. And here again for the mandrel image, as we see on the bottom, the extended FACS with much better performance than the FACS. We perform our comparison between the three algorithms in two terms. First, the measure of quality, where we use the average amount of pheromone, and here we see that the best algorithm is FACS on the left for the Lena image and on the right for the mandrel image. And this is sure because we are initializing on selected initial positions, so there is a lot of intersection between the solutions we are producing. And the second comparison we do is in terms of time complexity, and we see here that our two algorithms performs way better in terms of time complexity than the normal or traditional ACS. And this is also related to the pheromone update or simplifying the pheromone update because of reducing the number of pixels we are working with. In conclusion, we have proposed two algorithms or two modifications based on ACS system to solve the fundamental problem of edge detection in images. We we were able to solve with our second algorithm stagnation problem and to provide, using both algorithms, high quality solutions free of noise and with reduced complexity. Thanks for your attention.